Math 1332, Chapter 10, Probability and Counting Techniques. Section 1, Basic Concepts of Probability. Video 5, Complement of an Event. Complement. We've heard that word before. Suppose E is an event from a sample space S. Let that sink in. S is all the possible outcomes to an experiment. E is some of those outcomes. We can define a new event called the complement of E, denoted as E prime. That's how you could read that. E prime. Where have we seen that before? Anyway, but we'll read it E complement. We'll not bring in the notation used in calculus. So let me read that second sentence again. We can define a new event called the complement of E, denoted E complement with an apostrophe. E complement is the set of all outcomes in the sample space that are not in E. Seriously, does this sound familiar? If you're starting to have flashbacks to Chapter 2 set theory, you should. Because back then we defined the complement of a set as the set of all elements in the universe that were not in the original set. Well, if you think of the sample space as the universe, this is the exact same definition. So the complement of E is basically all the outcomes that are not accounted for in event E. Let's take a look at a quick example. Suppose our sample space is 1, 2, 3, 4, 5, 6, 7. So we're rolling a 7-sided die, if you will. And event E is the set containing the outcomes 1, 2, 3, and 5. Find E complement. Well, the answer wasn't supposed to be showing there, but just for kicks, just pretend you didn't see it for a second. What is the complement of E? Well, the complement of E would be everything in the sample space that is not accounted for in event E. So you could go to the sample space and say, well, we don't want the 1 because that's already accounted for, don't want the 2, don't want the 3, and don't want the 5. And the remaining elements would be your complement. You don't have to physically circle and cross out like I did, but I just wanted to give a visual to show you how to find the complement of a set. You go to the universe, sample space, cross out all the elements of the original event, and what remains is the complement of the event. It's the exact same definition as the complement of a set, just in the context of sample space and outcomes. Let's refer to the previous example, where our sample space was 1, 2, 3, 4, 5, 6, 7. Event E was 1, 2, 3, 5. And E complement was, that's not right. How about 4, 6, 7? Do you see why these two are not complements? If there were complements, then everything that's missing from E would be an E complement. E complement should have 6. But there's another reason they're not complements. E complement has something it's not supposed to have. E has 2, so does E complement. Think of it this way. 2 sets are complements if their intersection is empty, but their union is the universal set. Oh, I'm sorry, we're in probability. Let me try it again. 2 events are complements if their intersection is empty, they have no common outcomes, but their union is the entire sample space. Let's calculate some easy probabilities, shall we? Calculate the probability of event E. Remember, at its very core for theoretical probability, the probability of an event is the cardinality of that event divided by the cardinality of the sample space. Our event contains 4 numbers. Our sample space has 7 numbers. The probability of the event is 4/7. What about the probability of the complement? Well, the fact that it's the complement doesn't change the definition of theoretical probability. It's still the cardinality of the event, which in this case is the complement, divided by the cardinality of the sample space. But this time, it's not 4/7, it's 3/7. And then the question that may not be obvious, do you see a relationship between the probability of E and the probability of E complement? Well, they're both over 7, but that makes sense. They were destined to have the same denominator on the outset, and being a 7, it won't reduce unless it divides into a whole number. However, what do you get if you add these? You get 7 over 7, which is 1. And if you think about it, it makes sense. Because let's say I ask you to pick a number from 1 through 7. So that would be the sample space. In other words, if I say pick a number from 1 through 7, these are all the possible answers you can give me, unless you wouldn't try to be cute and say something like 2.7, in which case I'll say pick a whole number between 1 and 7 inclusive to remove all those shenanigans. But if I say pick a number 1 through 7, either it's in the event or it's not. And if it's not, then it's in its complement. So it's either got to be in the first one or it's got to be in the second one. In other words, being in an event or its complement is a certain thing. You pick a number from 1 to 7, it must be in one or the other. And that's why the joint probability, if you will, is 1. But it's not a coincidence. From the previous example, we have evidence that the probability of an event plus the probability of the event's complement is equal to 1. But is this always true? This is where you push yourself from being a person who follows somebody else's lead in math to somebody that can take the lead yourself. It's one thing to go, oh, that must be true. It's another thing to sit down and prove it for every case, not just one specific case. So how do you prove something in general when you have a specific example? The answer is you try to remove as much specificity as possible, usually in the form of removing numbers and replacing them with generic numbers, aka variables. So let's see if we can prove this from a theoretical perspective. Let's suppose S is a sample space with A outcomes, so that the cardinality of S is equal to A, whatever number that may be. And let's let E be an event with B outcomes, whatever number that may be, so that the cardinality of E is equal to B. That's all we're saying. We're counting up the things in the sample space and we're calling that answer A. We're counting up the things in the event E and calling that answer B. Since E complement contains all of the outcomes that E does not contain, okay, then E complement, excuse me, then E complement must contain A minus B outcomes so that the cardinality of E complement is A minus B. I think I'm out of my homemade apple and carrot juice. Ooh, but that stuff is good. Let's go back in the previous example and see what I mean by this part right here. That E complement must contain A minus B outcomes. In the sample space S, how many outcomes were there? There were 7 outcomes. In event E, how many outcomes were there? 1, 2, there were 4 outcomes. 7 minus 4 is 3, which accounts for the other 3 outcomes from the sample space that weren't accounted for in the original event. So that's all that highlighted thing is saying, is that if you know how many outcomes are in the sample space, we're calling it A, and you know how many outcomes are in the event, we're calling it B, then the difference is how many outcomes are in the complement. And it has to be A minus B because, as we discussed in the previous video about 3 properties of probability, the event cannot have more outcomes than the sample space. So if we turn the subtraction problem around, it would come out backwards. So what does all this mean? Let's highlight all the cardinalities that we have, because our theoretical probabilities are based on cardinalities, and specifically ratios of cardinalities. All right, so we're going to try to prove this. That was supposed to be drawn, not highlighted. We're going to try to prove this. Why don't we start with the left side? Probability of E plus the probability of E complement. Well, the probability of E is the cardinality of E, that's an equal sign, by the way, over the cardinality of the sample space. And the probability of E complement is the cardinality of E complement over the cardinality of the sample space. Well, we generically call the cardinality of E B. and we generically call the cardinality of the sample space A. And my apologies, I think there have been times in these videos that I've said sample size instead of sample space. That's just brain residual from teaching statistics too much. So if I ever say sample size, just assume I mean sample space. I digress. Where was I? Oh yeah, we just figured out the probability of E, which was by definition cardinality of E over cardinality of S, which was B over A. But now let's focus on that part, the cardinality of, the cardinality of E complement, which is the, try that again, the probability of E complement, which is the cardinality of E complement divided by the cardinality of the sample space. We already said the cardinality of the complement was A minus B. And we already know that the cardinality of the sample space is A. So that fraction represents the probability of the complement. Let me take off the highlights on the last two fractions. And let's think about the algebra that would have to go here. And I know this isn't an algebra class, but I firmly believe that every one of you can finish this off because of two things. Number one, you know the rule for adding fractions is get a common denominator, which we already have, which is A. And number two, in addition to, number one, in addition to knowing you get a common denominator, you should also know that you just combine the numerators. So we combine these. And number two, you probably know that when you add a number and its opposite, namely B and negative B, they cancel. So the only thing that survives when we add across the top is A, but A over A is equal to 1. Thus proving the claim that the sum of the probability of an event and its complement will always equal to 1. All right, that was neat, but what am I going to ask you guys to do? Well, we've already proven this, and by the way, this is equivalent to something else that's very important to point out. We've proven that the probability of an event plus the probability of its complement is 1, but if we did a little bit of algebraic shenanigans and grabbed the first probability here, and moved it to the other side, or subtracted it to the other side, if you will, then we would get this version of the same thing that says the probability of a complement is equal to 1 minus the probability of the event. Your brain already knows this, and I'm going to prove it real quick. If I said there was a 60% chance of rain tomorrow, what is the percent chance that it won't rain? 60% chance that it will rain, which means 40% chance that it won't rain, 100% minus 60%. Your brain already knows the second thing that I've highlighted, that if you know the probability of something happening, I can easily calculate the probability of it not happening. So let's take a look at an example. A survey shows 72% of US-born citizens currently live in the state in which they were born. I totally made up that statistic. What is the probability a US-born citizen does not live in the state in which they were born? Well, we have two events. We pick a person, we ask him a question. Do you live in, we pick a US-born citizen and ask him a question. Do you currently live in the state in which you were born? So currently live in the state in which they were born as an event. Does not live in the state in which they were born is the complement of that event. When we were told that 72% of US-born citizens currently live in the state in which they were born, we were told that the probability, actually before we do anything, let's call this event E, which makes this event E complement. We were given that the probability of E is 72%. Now, if you want to leave it as a percent, that's fine. If you want to turn it into a decimal, that's fine. I'm going to turn it into a decimal only because this formula up here involves a decimal number in the form of 1. If you wanted to do this formula as a percent formula, you would change the 1 to 100%. But let's go with decimals. We were given that the probability of E is 0.72. So the probability of E complement is 1 minus 0.72, which is 0.28 or 28%. Now, will the homework want percent or decimal? It should tell you. Just remember that if you do this formula, then with percents, then you need to treat that one like a 100%. All right, let's take look at one more example. The probability a student will pass a class is 3/5. What is the probability they will not pass the class? Again, you can probably look at this and already say the answer. But I want to make sure you're clear how this fits into what we just said. Pass a class and not pass a class are complements. We go to a bunch of students and ask them, did you pass the class? Either they belong to this event or they belong to that one. If we call pass the class E, then not pass the class is E complement. And we were given that the probability of E is 3/5. So the probability of E complement is 1 minus 3/5. If you want to get a common denominator and call it 5/5, that's fine. It may be easier to see that the probability is 2/5 that they will not pass the class. All right, one more video in this section and then we're done with it.